Hello, my name is Matthew Farah-Beltran, and this is my Lab 5 adventure. The purpose of this lab was to predict the motion of a falling slinky while tracking the effects of its surroundings. In the video, the guy on the right dropped the slinky from that height, and we had to determine whether the bottom of the slinky would stay stationary. So although we did observe some fluctuations in our data, the bottom of the slinky did remain stationary. So for some fundamental principles used in this lab, the first one is Newton's second law, basically stating that the change in momentum is proportional to the force applied. In this lab, we had the net force equaling the tension plus the gravitational force, and from this law, we can also derive position and velocity updates, which are used in our coding and calculations. Gravitational and tension force are also used, so the force of the slinky is representative of the tension force, which is also the opposite of gravitational force. So we can see in the formulas that the gravitational force is negative mg times the height, meanwhile the tension force is positive mass times gravity. As mentioned earlier, we took a YouTube video in which a man drops a slinky from a designated height, and we had to determine whether the bottom of that slinky would stay stationary while the top was falling. So using tracker, we found the slinky's position and initial velocity. So the position is the negative 1.6 to the power negative 3, y factor is 2.72 to the power negative 4, and the z is the 0 meters. So that was the initial position. Initial velocity of the slinky was 0 vector since it was dropped from rest. The spring also had a mass of around 0.218 kilograms, and using the left person as, I guess, like a scale, we found that the calibration height was 1.75 meters. On the right of the video, we can see our tracker graphs, and that kind of, I guess, alludes to the fact that the bottom of the slinky did stay stationary, as you can see from the GIF and the graphs. Here is my glow script code to simulate the video of the falling slinky. In this code, I inputted the initial conditions of the spring's mass, the initial position, and velocity, as well as the drag constant determined to be 75. So this drag constant basically includes the fact that the slinky is falling through the air, so there's going to be drag working against it, and through trial and error, we found that value to be 75. We also inputted factors such as time when the bottom of the slinky is the same, gravitational forces and the tension force of the slinky, as well as the velocity and position update formulas derived from Newton's second law. Additionally, we also inputted the delta t, which is the time until the slinky hits the ground, and again, gravitational drag forces and velocity and position updates. Here I've compared the results of both the observed and predicted position of the bottom of slinky, so what we found on the tracker video, as well as the coding simulation. So in both models, we found that the bottom of the slinky remains in place for about 5.5 seconds, and then after, which is the on the right side of the graph, the fall off, that's when the top reaches the bottom of the slinky and the whole slinky falls towards the ground. But overall, I do believe that the graph shows that the bottom of the slinky does remain in place. The plateau at the top kind of shows that the position stayed constant, and I do think that both models did a good job of showing that. However, there are some possible errors that could have occurred in this experiment, some of which being the observed motion being influenced by external forces not accounted for, so maybe stuff other than drag, gravitational forces, and tension forces, and also maybe I just didn't place the placement points precisely enough on tracker. But overall, the results do show that the bottom of the slinky does remain in place while the top falls down. For further analysis and thinking, I created a discussion question which states that what if the slinky had a counterweight at the bottom? So on the right, you see this amazing picture of myself and a slinky with a weight on the bottom. So what I concluded is that, like, if the weight or the mass at the bottom of the slinky allows for tension and gravitational force to still remain equal, or if the spring is long enough for these forces to again remain equal, then the bottom of the spring still will remain stationary when dropped. However, if the force of the mass is too much, then I do think that the bottom of the spring would fall before the top reaches it.